Hello everybody. In this video, we're going to be looking at what numerical partial differential equations are all about. So at this point, I'm going to assume that you've seen at least some information about maybe where partial differential equations can come from and what partial differential equations are. But in this video, we're going to look at one particular PDE, just for an example, basically, and we're going to look at what it means to do numerical analysis on that PDE, at least in the introductory sense. So a PDE is a differential equation that involves some function and its derivatives and some sort of partial derivatives. So derivatives in space, derivatives in time is usually what we're talking about. Now, the goal of classical PDEs is to find an analytic solution. So to write down a function algebraically that solves the PDE. The goal in numerical PDEs is to approximate the solution at typically some grid points along the domain. And then we want to figure out how much error we make and whether or not the solution is going to be stable. Let me kind of demonstrate that. So we're going to be dealing with the diffusion equation. The diffusion equation just imagines that we've got some concentration of, say, mass or heat energy or something like that, and it's just going to spread out over time. So ignore my code. You don't need to worry about my code at all. Let's say that we have a one-dimensional domain, 0 to 1, and we've got a high concentration or a high density of some gas or something. So say that this is like a perfume bottle is sitting here at 0.5, and there's a high concentration of perfume. Now the dots that you see here are the places in which we're going to make the approximate solution. So at every point in space where these dots are, I'm going to propagate forward in time and see what those solutions are. And I'm going to connect all the dots with straight lines. And if I have enough dots there, it'll fool you into thinking I've got some nice smooth curve. Now in the diffusion equation, we have some coefficient we can play with. So that diffusion coefficient dictates how fast or how slow the diffusion happens. So let me just play this one. And it's stepping forward every few time steps. You notice that the dots stay in the same locations, but as time goes on, the concentration, again, think perfume, is kind of diffusing out towards the walls. And maybe we'll say that we've got open windows here, so it's just going to kind of seep out the windows and we're never going to get a big accumulation at the windows. So that's with my diffusion coefficient set to 1 unit. Okay, and it's really slowing down at this point, so I'm not really seeing much. So let me run it again. So now I'm going to turn the diffusion coefficient way down. So it should diffuse much slower. So let's hit play. And sure enough, you see that it's diffusing much, much slower. Again, every one of these dots, I'm just saying propagate that dot forward in time using the numerical solution to the differential equation. And let's just see what the overall time dynamics are across the entire spatial domain. This is really what it means to solve a PDE numerically. Okay, well, let's run this again. We saw that at 1, it diffused kind of quickly. At 0.25, it was diffusing really slowly. So let's see what happens if I crank it up to like 1.75. I want to make this diffuse faster. Oh, and sure enough, okay, it's diffusing pretty quickly here. Things are diffusing pretty fast. At these early time steps on the other PDEs, it was still way up here somewhere. And it still looks like it's kind of diffusing in the way that we would expect. Oh my goodness! Oh my God! What's happening? Oh, it went completely unstable. And of course, yes, I staged this. So in this particular case, the PDE, the solution of the PDE went completely unstable and went totally haywire. It looked like it was behaving perfectly fine, but now 400 time steps in, it says that the concentration is times 10 to the 16. We have an infinite amount of perfume that has just pervaded the entire universe. Okay, something's gone horribly wrong. This is what I mean when we say determine a stable and accurate way to approximate the solution. Not all solutions are going to end up being stable. Well, let's look at this in 2 dimensions. Okay, this is the 2-dimensional heat equation or diffusion equation. And I've got the same basic setup here. So with diffusion coefficient 1, now in 2D, you can see all the grid points here. I've got a mesh of grid points, and in each one of those, I'm propagating those forward in time using my scheme to solve the numerical partial differential equation, or to solve the partial differential equation numerically. That's what I meant to say. And with diffusion coefficient 1, it's acting pretty good. 0.25, I cranked it down there. You notice it had diffused a little bit less at that point. And if I crank it way up to like 1.75, okay, it's already sunk down, and basically there's no more perfume there. Okay, well, let's run this guy again. And I'm going to turn the diffusion coefficient way up. And let's see what happens. Will this one go unstable in 2D? And what does it even look like? Oh, and there it goes, completely unstable, completely nonsense solution. Yes, so numerical PDEs are pretty fascinating in the sense that you can get a good solution for a short time, and it might blow up after some other time. And maybe you'll be able to get some solutions where it's good for all times. So this is what I mean by the stability and the accuracy. And of course, fast is going to be how much trade-off do you want to have on computational time. So numerical PDEs is a pretty fascinating topic. There are lots of other things other than the diffusion equation, the wave equation, the traveling wave equation. And of course, if you go further in this, there's things like the Schrodinger and the Navier-Stokes equations, Richard's equation, lots of really good PDEs out there that do really amazing, amazing physics and math. So we'll see you in the next ones.